What I've put up on the whiteboard is we have a laser with a fully reflecting mirror on this side, a partially reflecting mirror here, and I've identified three locations that we have within the laser. In the diagram right below it, you can see that I've now kind of expanded that drawing, and now here is position 1, here's position 2, and here's position 3. And what I have is I have three atoms, one at each of those locations, that are up in a metastable state at energy equal to E3. Now, this is not a natural configuration. Typically, always these atoms want to be in the ground state, so we've had what is called up here a population inversion. That is, we have atoms that are up in their metastable states as opposed to their ground states. And this is something that occurs because we've had pumping that's taken place in this laser. Now, to begin this process of stimulated emission, we have to have something called a seed photon in here. The seed photon must be of just a very specific energy. Its energy has got to be equal to E3 minus E1. Now, that seed photon could be generated somewhere else on this laser by just some kind of a spontaneous emission that occurs when this pumping has already taken place. So the seed photon moves down the axis of this optical cavity in the laser, and now here is where we start talking about stimulated emission. As this photon approaches or gets near this atom that's up in this metastable state, it interacts with this particular atom. It stimulates it to drop to a lower energy level or back down into the E1 level. The result of that is that if we call this photon 1, we end up with photon 1 coming off this direction, and we have photon 2, which now has been produced by this drop in energy of the atom from E3 to E1. Now here's what's significant. In stimulated emission, these two photons right here have some characteristics that are unlike most kinds of de-excitation that occurs within atoms. For one thing, they're unidirectional, meaning that they're moving in the same direction. The other thing is they're of the same energy. And the third thing, and very important, is that they are coherent. That means that they're moving in exactly the same phase with each other. And this, we know from having studied fundamentals of light and laser, represents the properties of laser light. Now, these two photons will continue to move down the axis of this optical cavity in the laser. One of the two of them will interact again right here with E3, or this energy level E3 in this atom, which is at location 2. The same thing happens again. This interaction stimulates this atom to drop down into its ground state. The result is that a photon P3 is produced, but P1 and P2 still exist. So you can see we started with one photon here, we have two photons here, we have three photons here, all of which are unidirectional, have the same energy, and are coherent. Again, as we move from location 2 to location 1 in this laser, one of these three photons interacts with this atom. It again stimulates it to drop down into its lower energy state. Same result again occurs, and that is that we end up with a fourth photon being produced. That goes with the first one that was produced, and the second one that was produced, and the third one that was being produced. So we start with 1, we end up with 4, and you start to see now this amplification effect that takes place inside a laser. And this is one of the key aspects of what stimulated emission allows you to be able to do. Now, as you approach this fully reflecting mirror here, you know that what's going to happen is that these photons will reflect off, they'll change their direction, and they'll start moving back into the optical cavity again. At the very end of this process, again, here's a partially reflecting mirror. Some of these photons are going to escape out. Remember that they are all unidirectional. Again, moving in the same direction. They are of the same energy, and they are coherent. And of course, that represents the laser light that is the output that results from our system that we have up here and from this optical cavity. So I think you now see the importance of this stimulated emission in that it is a process that creates more photons. It is a process that allows us then to create special kinds of photons that have these properties, and of course that represents laser light and represents the output that we're after in a laser system.